All right, welcome to this explainer. Today, we're taking what might look like a dry, dusty textbook concept from analytical chemistry, and honestly, we're turning it into a pretty wild, high-stakes mechanical journey. We're talking about ion chromatography. Now, if you've ever wondered how on Earth scientists can pinpoint and measure tiny polar molecules hidden inside incredibly complex mixtures, well, you're absolutely in the right place. We're going to kind of shrink ourselves down today and literally follow the journey of a single ion as it navigates through what is, frankly, a truly remarkable piece of engineering. Let's get into it.
Okay, let's dive right into this. Here's our roadmap for the journey. First, we'll meet ion chromatography, then navigate the corrosive mobile phase and tackle the stationary phase obstacles. After that, we'll break down the separation principle, face the conductivity challenge, and finally, look at the brilliant suppressive solution. Section 1. Meet ion chromatography, a close cousin to HPLC. So, ion chromatography, or IC for short, is this incredibly powerful analytical technique we use to measure polar species, whether they're organic or inorganic. Now, just like HPLC, it involves pumping a sample through a system to separate out its components. But IC needs some very special attention because ions act a little differently. Think of the layout of this instrument as our treasure map for the day. Our sample's journey kicks off as it gets injected and pumped along by the mobile phase. It travels straight into the column, which is really the heart of the separation. Then it passes through a highly specialized component called the suppressor, before finally hitting the conductivity detector where it gets recorded.
Moving on to Section 2, the corrosive mobile phase, navigating the chemical river. Let's contrast the two main physical environments in this system. The mobile phase, that's our river. But listen, this is definitely not some gentle babbling stream. It's an aqueous ionic medium, and it is highly concentrated. We're talking about highly corrosive acids or intense alkaline entities. It's just a totally extreme environment designed to ruthlessly push our sample along. And because this river is so incredibly hostile, the riverbed, which is the stationary phase, has to be tough, like really tough. The whole system is built out of inert solid materials, often these complex synthetic resins, built specifically to withstand crazy extreme pH conditions without just falling apart.
Section 3. The stationary phase obstacles, building the riverbed. And to understand what that obstacle course looks like up close, at a microscopic level, it's typically made of synthetic copolymers, things like cross-linked polystyrene and divinylbenzene. Basically, we've got these tiny hard spheres, just a few micrometers in diameter. But they aren't just plain pieces of plastic. Their surfaces are chemically modified to introduce specific acidic or basic functional groups. Essentially, they're completely covered in ionic sites, acting like these tiny little electrical traps, just waiting to grab onto the ions in our sample as they come rushing past in that corrosive river. So the really crucial point here is how these little traps actually work. And it all boils down to one concept: charge density. Charge density is simply the measure of electrical charge per unit of volume for any given ion. And in this system, it dictates absolutely everything. The higher the charge density of a sample ion, the stronger it interacts with those oppositely charged sites on the stationary phase, which means it gets stuck there for a longer period of time. By exploiting these tiny differences in charge density, we basically create a staggered finish line. Different ions from the exact same sample are going to travel through the column at different speeds, which effectively separates them out.
Section 4. The separation principle. The reversible equilibrium.
All right, let's walk through this process step by step. First, our sample enters that highly ionic, super corrosive mobile phase. Second, as it pushes through the column, the sample ions start interacting with those stationary phase ionic sites we just talked about. Third, the ions get temporarily retained, snagged in those electrical traps, strictly based on their unique charge density. And finally, step 4, they don't stay trapped forever. The mobile phase is already packed with its own counter ions, like carbonated species, and these are constantly fighting for those exact same traps. Eventually, these counter ions displace the sample ions, kicking them back into the flow. It's this continuous reversible exchange. And what's actually super fascinating is that this exchange process happens way slower than what you'd see in other types of chromatography. It takes some very deliberate engineering to optimize.
Section 5. The conductivity challenge. A whisper at a rock concert.
Now, I want you to really think about this for a second. How do you detect one tiny microscopic sample ion when it's drowning in a sea of incredibly noisy background ions? Because remember, our mobile phase river is totally packed with highly conductive electrolytes just to push the sample along. And we're using a conductivity detector at the end of the line, right? Which measures the electrical conductance of the fluid. But since the mobile phase is already so heavily loaded with ions, its background conductance is just deafening. Trying to pick up the tiny electrical signal of our specific separated sample ions in that mess, it is literally like trying to hear someone whisper at a heavy metal rock concert.
Oh, and the difficulty doesn't even end there. Because conductance is so wildly dependent on temperature, the detection cell requires absolute, impossibly strict temperature control. Like how strict? We're talking down to a variance of just 0.01 degrees Celsius. No joke. If the temperature fluctuates by even a tiny fraction of a degree, the baseline signal spikes, and boom, our delicate measurement is completely ruined. But here is what we're ultimately chasing. A beautiful, perfectly clear chromatogram that shows the distinct separation of organic acids in a sample. To get a graph this crisp, this clean, that massive background noise, all that ionic loading from the mobile phase, has to be almost entirely wiped out before the fluid actually hits the detector. Somehow we have to mute the rock concert right before the whisper happens. Which brings us to Section 6, the suppressor solution, the hero of the machine. Now, what's really interesting here is the physical placement. The suppressor is this genius device inserted directly between the separation column and the conductivity detector, and its entire job, its sole purpose in life, is to pull off an absolute chemical magic trick on the fly. And here is exactly how that magic works. The suppressor uses functional groups with a charge that's opposite to the ones used in the separation column. So as that highly conductive mobile phase exits the column, the suppressor essentially forces an acid-base neutralization reaction. Let's say you're using hydrochloric acid as your mobile phase. The suppressor steps in, strips out the highly conductive chloride and hydrogen ions, and reacts them to form just plain neutral water. Boom! The deafening rock concert is instantly silenced. But it actually gets even better. This exact same process amplifies the signal of the targeted sample ions. So a sample ion like sodium doesn't become water, it pairs up with hydroxide to become sodium hydroxide, which is highly conductive. So it literally turns up the volume on the whisper right as it completely silences the room. It's brilliant. Now, early suppressors were honestly just secondary columns, but they had these massive dead volumes that kind of ruined the separation efficiency because they let the nicely separated ions mix right back together. But today, we use these incredibly advanced fiber or micromembrane suppressors. These absolute marvels of engineering reduce the dead volume to a mere 50 microliters. And even more impressively, modern auto-regenerating suppressors use the continuous electrolysis of water to produce the regenerating ions right there in situ. This means they can run continuously during a gradient elution without you ever needing to stop the machine and manually recharge them.
And there you have it. The journey is complete. We've followed our sample from being dropped into this chaotic, corrosive chemical river. We've watched it navigate the precise, tricky electrical obstacle course of the resin beads, witnessed the sheer engineering brilliance of the suppressor neutralizing all that background noise, all of it ending with a perfectly clear, readable signal at the conductivity detector. It is just an astonishing feat of analytical chemistry. Which leaves me with a final thought for you to ponder today. If human engineering can devise a way to quiet the deafening electrical noise of a highly corrosive chemical river just to hear a single microscopic molecular whisper, what other invisible systems in our world could we map out if we applied this kind of relentless engineered clarity? Thank you so much for joining me on this explainer today. Keep questioning, keep learning, and I'll see you next time.